We're going to do a couple more examples with Markovnikov hydrohalogenation to show about when we form a chiral center. So what happens? Let's draw an alkene here. Now that what we learn about Markovnikov rules in regioselectivity of hydrohalogenation is then that we form the more stable carbocation, and we have first the proton transfer step, in which you're going to add the hydrogen at the least substituted so that you form the more stable carbocation. So adding the hydrogen here is going to produce the following carbocation. When you have that, the next step is a nucleophilic attack by bromide. Now, remember that the hybridization, when you have a carbocation like that, the hybridization of that carbon is sp2. And by being sp2, remember these three are bonds in one plane, in the MCP orbital, say, is perpendicular to the screen. So this on the screen, and in the p orbital that's empty, perpendicular. So we can have the nucleophilic attack from above the plane and from below that plane. And that will lead us to two products. So now I'm going to draw that. Say that the attack was from above the plane. I'm going to get the following. And that's one possibility. The other is that if bromine attacked the opposite side, so you are going to get the following. Bromine, and that's H. These two are enantiomers. I made a mistake here. Enantiomers. And having the same chance of attacking on either side, this is likely to be a racemic mix. Racemic, I'm doing a lot of misspelling here. Racemic mix. So a 50-50 mix of enantiomers. So we need to keep in mind then that whenever we're forming carbocation, what is the geometry? And if we have that nucleophilic attack and we're producing chiral centers, keep in mind that you're forming two enantiomers. It's not one product, it's two. So regioselectivity is still Markovnikov, you're adding the H at the least substituted, but then the nucleophilic attack can happen on either side of the plane. Now I'm going to do one more example with a structure that's somewhat similar, but we're going to see another important factor that we need to keep in mind when we are producing carbocation intermediates. And so let's look at the following. Now, okay. So now I'm going to draw something else. There's a double bond here, and I have that. Okay. That's my structure. And so again, I'm going to do a hydrohalogenation. So I'm going to do HBr, one we commonly use. And so what's the first step? We said the first step is a proton transfer. So pi electrons acting as a base. And this is going to go here. Regiochemistry, we know is going to be Markovnikov because we want to generate the more stable carbocation. So we're adding the H at the least substituted, and the carbocation is going to be here. The alkene right here is mono-substituted. If we look at the carbon on the side, there's no substituent. This is H and H. And on the other side, we have one substituent and one H. So this is a mono-substituted alkene. All right. But still, we're keeping our regioselectivity Markovnikov in the sense that we want to produce the more stable carbocation. So H here, carbocation is going to be here. Now, what type of carbocation is that? That is, look at this carbon, one R group, another. So that is a secondary carbocation, not the most stable. But other things can happen with carbocations. Carbocations can rearrange. So I here have a hydrogen. So I have metals, and I'm missing one carbon here from that structure. Yes? So that's the part I was missing, this one here. Okay, but now I have my metal group. Again, I have a hydrogen. It wasn't pictured, but still there. So in that, we can have here a 1,2 hydride shift. What that is hydride, we are moving the H with the electrons, migrating 1, 2. In doing so, we're making another carbocation. What is a carbocation in this case? Since we're moving the hydride over there, now the charge is going to be here. So notice now that we have produced from that rearrangement a tertiary carbocation. Now, this process is irreversible. You get them from a secondary, a tertiary carbocation. So the major product then is going to be when you have the nucleophilic attack over the more stable carbocation. So you need to do the rearrangement, and that's then your major product. Since we are not making a cutoff center, we're going to have one product, which is going to be bromine and metal. Okay, so things to keep in mind when we're doing these reactions is Markovnikov regioselectivity is because you want to form a more stable carbocation. Second, we need to keep in mind that the geometry of the carbocation is trigonoplanar, and if we are creating a cutoff center, the product is going to be a racemic mix. Another thing important to keep in mind is that when you are making carbocations in the reactions, carbocations may rearrange, and they will if you can produce a more stable carbocation. That is going to be your major product.